So we can rotate regions around axes other than the x and y axis. So for instance, in this video, we're going to rotate a region around the line y equals 4. And we're going to see how that plays out in our analysis here. So first we sketch our region. Y equals x squared looks like this. We're sketching it on the interval 0 to 2. Now it says the region between the graph x squared and the line y equals 4, which suggests, here's y equals 4, and here's x squared, so it's describing this region here. Okay, and so we're rotating that around that axis. So what we need to do is, as usual, draw a rectangle. I'm going to draw a vertical rectangle here. That'll be the sort of the arbitrary rectangle. Now when you spin that around that axis, we get our disk. So as usual, because it's a vertical rectangle, we're integrating with respect to x, because we're going to be summing all these disks along the, as x goes from 0 to 2. So that's a dx. The next question we have to answer is, what's our radius? And this is where you have to be a little thoughtful. So our radius, you would agree, is this length right here, right? Imagine rotating that around that axis y equals 4. That would be that length would be the radius. So we need to describe this radius, and we need to describe it in terms of y values, right? So it has length. How do we find length in the coordinate plane? We do it through subtraction. So this y value here is 4. This y value here is not going to be a number. It's going to be an expression. So that point has coordinates x, x squared, since it's on the curve. So this distance is going to be 4 minus x squared, right? I mean, just like I often use this example, think about finding, if I asked you what this length was right here, you would just do 4 minus 1. That's all we're doing. So 4 minus x squared is the expression for the radius. And now I know that my volume is pi r squared times dx, and so my total volume is going to equal the integral from 0 to 2 pi 4 minus x squared times dx. All right, so subtle nuance here, rotating around axes other than the x and y axis. Let's try revolving around a vertical line that's not the y-axis. So the region between y equals x squared, the x-axis, and the line x equals 2. So x equals 2 is a vertical line. So the region between the graph of y equals x squared, the x-axis, and x equals 2, that's this region. That is going to be revolved around the line x equals 2. And so our goal is to find the volume of that solid. Well, this time it makes sense to draw a horizontal rectangle. If we want this to be a disk, you always want your rectangle to be perpendicular to the axis of rotation. So we get a disk situated like this. Since it's a horizontal rectangle, we need to integrate with respect to y, so that's a dy. And that means we need to name everything, we need to name all the points in terms of y. So this point right here, for instance, we know we can call it x, x squared, but that's not the name I want. I want to call it square root of y, y. And again, square root of y coming from the fact that you would just square root that to solve for x. So the x coordinate of any point on that curve is square root of y. So now we think about the radius here. The radius is this length here, but that's a horizontal length, which means we need to subtract x values to get that answer. So the right x value is always a 2, and the left x value changes, but it's a function of y in this case. So it's the square root of y. So subtracting x coordinates, you get that this length will always be expressed as 2 minus the square root of y. So there's my r. And so now I can say r is 2 minus the square root of y. and now it's all just sort of exactly the same as they've always been at this point. That was really the hard part. So it's pi r squared dy, and so the total volume, when we sum up all these disks, is the integral from 0 to, so from 0, this is where we're integrating with respect to y. We're integrating from y equals 0 to y equals this intersection point, which we know is 4, because when x is 2, y is 4. So from 0 to 4, pi r squared times dy.